Okay, hello, hi everybody. So welcome to the second Tuesday session. So we'll paraphrase maybe yesterday's comments, so you can speak in any language you want as long as English. So I hope you'll be in the right place. So our first speaker will be Maciej, Skórski, and he will talk about statistical inference for elementary oscillator-based true random number generators. So the first, thank you.
Thank you. Before going into details, I would like to say that I very appreciate the effort made by organizers to provide financial support for participants. I am one of them who received this, and that is a great thing to be here on this conference and receive this funding. Thank you. My talk is going to be about the very foundational problem, important for cryptography and beyond. I believe this is one of those problems that are very easy to state, very easy to paint as a figure, as a plot, but quite non-trivial to analyze. And I hope that one of these conference outcomes could be some interactions with some of you who would provide me some further expertise how to solve those problems. So what are those problems? We start with a brief introduction. This work is a joint work with my French colleagues. From time to time, I get invited to a French lab, which is dedicated to actually build and test hardware-based random number generators. So actual devices like boxes inside, there are some smart things that produce electronic signals, and those signals get digitized, analyzed, and random numbers in form of random sequences of 0 and 1's random bits essentially are extracted. So I'm very happy to be their frequent guest and to learn about electronic principles and stochastic modeling that are behind the modern design of true random number generators. And it is my intention to give you a taste of how those designs look like, what are modeling challenges, and what are some open problems in this area. Few sentences of motivation. Cryptographic quality randomness comes usually from jittered signals. So to get randomness of really high quality, we don't use those compromised dynamical systems like congruential generators or reading fractional parts of a simple dynamical system like square root of 2 multiplied by integers. It doesn't work. It produces chaotic patterns, but they are not truly random. The opposite. In order to get and extract cryptographic quality randomness, we need some noise that comes from some physical phenomena. That could be radiation, that could be noise from like thermal noise from electronic chips. This sort of things is better suited for to generate cryptographic quality randomness. Jitter is another word that is of critical importance. Jitter means that those signals, usually we can think of them, most of them, as square-like waves, but they are perturbed. That means that subsequent rising and falling edges appear not regularly, but at slightly random times, slightly sooner or slightly later. And essentially, this stochastic perturbation of signals is what enables generating an extraction of randomness. And this jitter is actually an artifact. So manufacturers don't want this jitter to be produced by their devices, by their chipsets. It's an unintended effect from the manufacturer's perspective, which, however, can be exploited by researchers, by scientists, by cryptographers. So, in a way, there is a race from manufacturers to reduce the level of jitters in devices, and between researchers who would like to exploit this unintended but very useful from the random number generating perspective phenomena. To build a modern generator, we need essentially to understand what this jitter, how this jitter can be modeled, and how we actually can extract random bits, because there is going to be a gap between just the signal, even modeled stochastically, and the actual sequence of 0 and 1 merely random bits. So to explain the very principle of elemental ring oscillators, which are thought to be the simplest design, yet still full of challenges. Let me present this full plot. Basically, we have two signals. One is the signal which is actually sampled on the top. One is the signal which is used as the reference signal, the clock. So you actually sample one signal with another signal. And if you have a look at the picture above, the scale maybe doesn't make it very visible, but the subsequent periods are not equal. They are slightly perturbed. This is perhaps more visible and obvious if we confirm this with the figure below. So in red, we have a reference clock, and we just read samples from the target signal at the rising edges of the clock signal. So this is first rising edge, and I land at -1. This is the second rising edge, and I land at 1. Third rising edge of the clock, and I land here. Fourth rising edge, and I land there, and so on. Another rising edge, I land at -1. Another rising edge, and I land at -1. And finally, this line is missing. Here is another rising edge of the clock signal, and I land at 1. But those two plots on the left and right get randomly perturbed. And one visible difference is that the point in the middle, which once belonged to the upper part of the signal, due to the perturbation actually lands below. And this is a perfect example of how those things work in practice. So this jitter that perturbs the period, the phase frequency, actually flips certain bits. It is just a matter of time and actually a matter of exact properties of the stochastic process, how long we'll be waiting for this phenomena, how frequent, and so on. But this particular design, ring oscillators, assumes that the jitter follows a random walk paradigm. That means that the jitter accumulates over time, and the further we go, the more frequent this phenomena happens, and the more easy to get my bits flipped. And this is what is happening here just for artificial numbers. If there was no jitter at all, then we would get a locking pattern, right? Because frequency 7 against frequency 6, after 42 observations, like cycles like that, everything would repeat if there was no jitter. But due to the jitter, we are actually able to produce randomness from the signal in no return. So this is it. We can, of course, have multiple designs beyond ring oscillators. Even ring oscillators can produce certain components in its spectrum are modeled differently, but for simplification, and that it is believed that the dominant component is actually given by the random walk. So as long as we use ring oscillators, we can actually assume that we have this picture with the jitter accumulating according to the random walk principle. And this is a script that I attached that can be used to generate this example. Now, let me get deeper into modeling details. So the general principle is that I have a periodic signal in form of a pulse wave. It has its basic base frequency, but that frequency gets perturbed by the stochastic process, random walk, Brownian motion in the case of ring oscillators. And we can assume, this is another trick that is used in practice, that the clock signal is jitter-free. This is essentially that was the case of this figure. Jitter was applied to the upper part, but the lower part was assumed to be jitter-free. In reality, both are jittered, but the trick is to, for modeling purposes, to shift the jitter from the clock to the target. So we actually compensate for some deviations here by multiplying the variation here. And we still get stochastically equivalent results. This is the trick. So our clock is jitter-free. And the jitter in the upper part is going to accumulate according to the Brownian motion. And related work is quite significant because this looks like a very basic and interesting problem. But essentially there are two approaches. One approach is to consider those signals as linear processes. Then I just model what is the next time when the rising edge arrives. And this next time is every time a little different, like waiting for a bus at a bus stop. This is one approach, but more, I would say, a cleaner approach and somehow more successful was to model the phase at every time point, even at points that are not actually sampled. So fully continuous stochastic process. And that was a kind of great discovery because it enabled some full approximations. And those approximations were derived by applying Fourier techniques. And my contribution, my small contribution I'm going to talk about in some more detail is built on top of that idea, except that I will apply different techniques than Fourier-based. Now, about techniques, because even if we understand the signal properties, even if we are fine with simplifications like jitter-free assumptions in the clock, like random walk model, we are still missing one critical part, which is what constitutes random bit. And the random bit can be simply defined by reading if the upper signal is in its upper or in its lower position. Pretty simple. And if we consider the phase of the signal, this is again pretty simple because it is just the decision if it's the first half or its second half. So a nice figure for this case is that I consider a random walk and I'm looking at its fractional part, at its first binary digit. If the first binary digit is 1 or 0, this decides what is the output bit. So we imagine that we have a Brownian motion with a drift. We are simply looking at the first binary digit. And of course, this, because of the variance accumulation over time, those digits converge to nearly unbiased case, 0.5, after taking enough samples. And this is essentially the idea how to extract one of the ideas. So we just need to wait until this uncertainty becomes that big that it will be nearly equally likely to land in the first or the second part of the period. Essentially to equally likely to produce 0 or 1. This approach, reading, waiting, and sampling after long enough time will produce nearly unbiased bits, of course, at the price of wasting those samples that have been skipped. But it works. The problem that I'm going to explore in more detail is to give more accurate approximations to this system and to at least think about alternatives to extraction techniques. So just to recall, we can think of a Brownian motion that starts at a certain location and that has a drift, that has its variation, and that Brownian motion is models the phase of the signal. Now, depending on if the phase has its fractional part between 0 and 0.5 or above, we are going to output 1 or 0. That's our system. And what can be achieved in this case is perfectly accurate finite dimensional probabilities and closed form formulas, an efficient implementation for numerical integration, and work in progress. In my case, is still what is still open are extractors and some asymptotic formulas for the entropy base. So what about those finite dimensional probabilities, and here is a very interesting relation. Namely, our distribution, our stochastic process, this fractional digit is related to a well-known object in mathematics, Jacobi's theta function. So Jacobi's theta function can be used to give an analytic description. I'm not sure if you have ever seen this before, but basically it is an older result. People some time ago analyzed problems like fractional digits of Gaussian-like distributions, because it's pretty cool and pretty foundational actually. So you can imagine having a Gaussian curve, and let's say that you paint gray, white, gray, white, gray, white every second half of the interval. And what is the probability? What is the difference between gray and white areas? So those problems are very natural. They are actually can be thought as coming from recreational mathematics, but apparently are very applied. Anyway, something has been developed, some machinery to attack this kind of problems, and then Jacobi theta's function arrives as a part of the solution. And that Jacobi theta function can give us the distribution of the fractional part. Essentially, that's the distribution of the phase of my signal, not the bit, not the 0 1 bit, but the phase. That means the specific location at every time point. If I know this, then it's just a matter of applying the Markovian property to derive the final formula for probabilities of bit sequences. So because I know the phase, I just need to apply modulo 1 and decide if this falls to the first or to the second half of the interval. And this can be derived for every finite tuple of bits. So essentially, I have a full solution to this problem. I can give the precise analytic description of bit sequences. There is some challenge. I'm going to touch on this soon, related to the numerical properties of this formula. Because one thing is to actually write down the smart formula, another thing is to be able to integrate it. And to integrate it, we can transform it a little. Now it's more apparent what kind of correlations appear in this formula, and perhaps what kind of integration methods can be successful to tackle this problem. So I have this product form, and every product term is potentially related to the term before and to one term ahead. So this is not an independent product. It is little correlated in terms of random parts that appear inside. Nevertheless, this still can be integrated numerically by a bunch of methods, and I had a table to support this claim. Basically, for some toy parameters, I give a description of probabilities assuming different starting conditions, stationary distribution of or fixed point locations. And this is just to highlight that numerically we can tackle this problem, and we can actually compute finite dimensional probabilities. So theoretically, this is nearly solved up to the fact that I would need more powerful integration, numerical integration, because the schema should be somehow adjusted to minimize the numerical error or provide some guarantees on the convergence. So this is still open. And it would be super cool to have rigorous formulas for asymptotic entropy rate, which is, in my case, still an open problem, subject of research. Sorry for jumping. But I wanted to come back for a moment to this point. So finite dimensional probability formulas have been derived, but to be fully satisfied, we would need more accurate numerical integration formula and some asymptotic simplifications, which to me are, as far as I know, and even my knowledge and my skills, it's still a little non-trivial. So the situation is that we have a very classical process, Brownian motion with drift. We are looking at these fractional digits. We can have finite dimensional probabilities. This is almost surprising. But what we are missing is to have very accurate integration formulas and to propose an efficient extraction methods. One thing which can be seen from this formula is that the naive way of extracting, that is skipping large blocks of bits and taking, say, every 10,000 bit, works, because then those deltas are relatively large. If they are relatively large with respect to the jitter level, then that term will be nearly 1/2. That means that if I sample points that are very, very distant, they are nearly unbiased. But this is still, it seems it is somehow overkill, overshoot, because I waste that many samples from the entire trajectory. So what bothers me, what concerns me is that there should be better ways to exploit the whole trajectory, not just wait until the walk converges and kind of restart it, but rather do something more clever, like take a parity over the trajectory or other tricks that could extract nearly unbiased 0-1 using less samples. And this formula is kind of novel for numerical integration, but even if it may be theoretically appealing, the problem is actually not fully solved. Because what is more interesting, what would be more interesting is actually to come up with the extraction method. So do something clever, more clever, than just subsampling distant points. And as far as this problem is concerned, I have no clue how to do that better. And this is my big open problem, with regards to which I would love to hear any feedback or receive any help, if that's possible. If you find this interesting, definitely I would be more than happy to discuss this in more detail. The numerical implementation that allows us to integrate numerically is actually nothing non-trivial. We just need to apply a special function, Jacobi's theta, and do some tricks to vectorize the problem to be able to compute this in a scalable way. So I'm going to skip this part. Rather, I'm going to highlight again that although I have obtained analytical formulas for finite dimensional probabilities, and also I did some problems on numerical implementation and integration, on my top priority list is something of much higher importance. It is to propose a cool way of extracting from those trajectories, not taking points that are far away, but do something more clever. And also to analyze limiting entropies, because the literature only knows some approximations, and this topic is still an active area of research. But from the point of view of applied people, this kind of work is actually something that supports the design of true random number generators. That means progress on this topic would for sure enable designing even more efficient true random number generators that use true, that are probably secure. So this is to highlight the importance of this topic. And once again, thank you. I'm very glad to be here speaking to you. Thank you.
We're now some time for questions. So anybody? Ask something? Okay, then let me start. Sorry, I'm not an expert, but if I understand correctly, you have the input data, which is essentially this Brown noise, right? And you want to somehow transfer it into the 0-1 sequence. So my first question is here, you assume in fact that your mean and standard deviations are known to you, right? So I guess in practice, they could slightly differ, change. Does this break the methods, or did you do some robustness study in respect to this?
Hardware engineers can set them on devices to some extent. Therefore, this justifies the assumption that they are known. I mean, they can be measured using oscilloscope and other tricks. Another way to estimate the parameters would be the maximum likelihood estimation, which would be based upon this formula. Because if I can evaluate the probability of generated data, assuming those model parameters, then I could apply maximum likelihood principle to find parameters that make my generated data most likely. And the formula is analytic. So that's another way of solving that. And both ways were actually tested. And this is kind of under control.
And then maybe a second follow-up question, because when you run a motion, the increments are effectively independent, right?
Yes.
So right now, why don't you use this directly in a sense, just consider increments and use inverse transform, you have a true noise, etc. While doing this whole machinery, right, with this?
And that's perhaps what I didn't highlight enough. We don't have the full access to the phase. We can only observe it through this discrete channel. That means that even if under the hood I have this Brownian motion, what I can observe in practice, I can only measure it through those square pulse waves. That is, what I really observe are those binary fractional digits. And this follows from this. So the stochastic process is behind this figure, but the only information I have essentially at the end is whether I hit the upper or lower part, and nothing more. And this makes this complexity.
Thank you very much. So another question? One more.
So I understand that you are generating, from a user perspective, I understand that using this methodology, you are generating sample from the uniform distribution. Correct.
I'm sorry, that I generate.
You are generating, your random number generates sample from the uniform distribution.
More precisely, nearly unbiased 0-1 bits. So 0-1 with 50-50.
So you may treat it as a double precision number. Normalize it and treat it as a uniform 0-1. Is that correct?
Yes. I mean, say that I would like a uniform number in this float 16 precision, yes, then I would take 16 outputs of this sort, concatenate them, and they would constitute my binary digits.
So have you tried to actually, because for uniform distribution, we know that we provide distribution functions. We try to run some statistical inference tests to check we are really getting true random uniform distribution.
Yes, we have entire batteries in crypto that do those tricks and even more, depending on the test machinery used. They are MIST tests invented by this American Standardization Institute, and they are more batteries, and they apply different tricks. They analyze periodic patterns by Fourier methods. They analyze autocorrelation. Maybe your particular strategy of looking at uniformity of entire blocks is not implemented as a single test, but I believe that diversity of those batteries make it somehow equivalent. In fact, usually we also look at other tests, so we don't end up with standard things, but we analyze even more. And this is actually a very interesting trick. Thank you. I will, next time I will run those batteries, I will add it to see if it will make any difference. But we do that in addition to other efforts to obtain proofs.
Thank you.